There's a machine so complex that only one company on Earth can build it. It weighs 180 tons. It ships in 250 crates that require 3 cargo planes. It fires a laser at droplets of molten tin, 50,000 times per second, generating plasma hotter than the surface of the sun, all to etch circuits thinner than a strand of DNA onto a sliver of silicon. And right now, in a secret laboratory in Shenzhen, a team of engineers working under fake names and camera surveillance has built a prototype of this machine. By reverse engineering parts they bought on the black market. This isn't a spy thriller. This is the semiconductor industry in 2026. And what's happening right now will determine which nations control artificial intelligence, military power, and the global economy for the next 50 years. We're living through the most dramatic restructuring of global manufacturing since World War II. Governments are spending hundreds of billions of dollars. Not on weapons, not on space programs, on chip factories. The United States just attracted the single largest foreign direct investment in its history. $165 billion from a single Taiwanese company to build fabs in the Arizona desert. Meanwhile, China has reportedly spent over $150 billion trying to build a domestic semiconductor supply chain from scratch. These aren't just business decisions. They're acts of geopolitical survival. Because the country that controls chip manufacturing controls everything that runs on chip, which is increasingly everything. By the end of this video, you'll understand why a tiny Dutch company you've probably never heard of holds more geopolitical power than most militaries, why the Arizona desert is becoming the most strategically important piece of real estate in America, and why China's secret prototype could rewrite the rules of the entire game. For decades, the semiconductor industry was the crown jewel of globalization. It was elegant in its efficiency and terrifying in its fragility. Here's how it worked. Chips were designed in California, manufactured in Taiwan, assembled in Malaysia, and shipped everywhere. Each step was performed by the absolute best in the world at that specific task. No duplication, no redundancy. And at the center of it all sat one company, Taiwan's Semiconductor Manufacturing Company, TSMC. Today, TSMC produces roughly 60% of all contract manufactured semiconductor chips on Earth. But that number doesn't tell the real story. When it comes to the most advanced logic chip, the ones powering your iPhone, training ChatGPT, and guiding military systems, as TSMC manufactures about 90% of them. Not 90% of one country's supply, 90% of the planet's. Think about that for a moment. The technology underpinning the entire AI revolution, the military systems of every Western nation, the smartphones in 3 billion pockets, nearly all of it flows through factories on an island of 23 million people, 100 miles off the coast of a superpower that has publicly declared it will reclaim that island by force, if necessary. For years, this concentration of risk was treated like background noise. Analysts mentioned it in footnotes. Executives shrugged. Then 2 things happened in rapid succession that changed everything. First, the pandemic hit. Suddenly, car companies couldn't get basic chips. PlayStation consoles vanished from shelves. Hospitals couldn't procure medical devices. The world got a visceral, expensive lesson in what happens when chip supply chains break. And these weren't even the advanced chips. These were the simple ones. Second, the US-China relationship went from competitive to confrontational. In October 2022, the Biden administration dropped what one analyst called a technological nuclear bomb, sweeping export controls designed to cut China off from advanced semiconductor technology entirely. Not just finished chips, the machines that make the chips, the software that designs them, even the specific types of memory needed to train AI. That was the inciting incident. The moment the global semiconductor supply chain, decades in the making, optimized for efficiency above all else, began to crack apart along geopolitical fault lines. Before we talk about the massive factory build-outs and the geopolitical chess moves, you need to understand the single most important machine in the world that almost nobody knows about. ASML is a Dutch company headquartered in Veldhoven, a small town in the southern Netherlands. They make extreme ultraviolet lithography machines, EUV for short. These are the only devices on Earth capable of manufacturing chips at the cutting edge. 5 nanometers, 3 nanometers, 2 nanometers and below. Here's what makes ASML's monopoly almost absurd. EUV light is absorbed by air, glass, and virtually everything. It can only travel through a vacuum. So the machine has to create it artificially by blasting a high-powered CO2 laser at microscopic tin droplets at high speed. The resulting plasma generates extreme ultraviolet light, which then bounces off mirrors so smooth that if you scaled them to the size of Germany, the largest imperfection would be smaller than a millimeter. Each machine contains over 100,000 individual parts sourced from thousands of suppliers across the globe. The latest high-NA models cost over $370 million each. No country has ever successfully replicated this technology. Not Japan. Not the United States. ASML spent over 30 years developing it, nearly went bankrupt multiple times, and only survived because Intel, Samsung, and TSMC invested directly in the company to keep the program alive. This makes ASML the ultimate choke point. In 2019, under US pressure, the Dutch government blocked EUV sales to China. By 2024, restrictions expanded to cover even older, less advanced lithography tools. As of early 2025, the Netherlands expanded controls further to include specific measuring and inspection equipment. Then, in October 2025, the Dutch government did something unprecedented. It invoked emergency powers to seize control of Nexperia, a Chinese-owned chip manufacturer based in the Netherlands, to prevent transfer of critical technical knowledge. But here's the twist nobody expected. In a high-security laboratory in Shenzhen, behind layers of surveillance and secrecy, Chinese engineers have built a working prototype EUV machine. The project was led partly by former ASML engineers, recruited with signing bonuses reportedly as high as $700,000 plus housing benefits. Some were issued fake identity cards to maintain secrecy. The team sourced components by purchasing and dismantling older ASML machines from secondary markets. Huawei reportedly plays a central coordinating role, linking state institutions, private companies, and thousands of researchers in what observers have called China's Semiconductor Manhattan Project. The prototype was completed in early 2025. It can generate EUV light. It has not yet produced a functioning chip. Engineers inside the project believe 2028 is optimistic for chip production. 2030 is more realistic. And by then, ASML will have moved to the next generation of machines, meaning China's breakthrough, when it arrives, may already be a generation behind. But that misses the larger point. The fact that the prototype exists at all shattered the assumption that export controls could permanently bottle up Chinese semiconductor capabilities. Former ASML CEO Peter Wennink warned of this exact scenario in 2023 when he said the restrictions were forcing China to become innovative in ways nobody had anticipated. And while the world focuses on the EUV race, China has been quietly playing a different game entirely. SMIC, China's largest foundry, has developed 3 generations of 7-nanometer class manufacturing technology without any EUV access at all, using older DUV equipment and a clever technique called multi-patterning. China's self-sufficiency rate in semiconductors has climbed from 15% in 2019 to roughly 25% today. Chinese foundries are expected to account for over a quarter of global mature node capacity by the end of 2025, and there's a counterpunch that gets almost zero attention in Western media. Beijing controls the global supply of several critical raw materials essential for chip manufacturing: gallium, germanium, rare earth elements. In response to Western export controls, China has strategically restricted exports of these materials, creating its own choke point in reverse. You can't build chips without these materials, and for many of them, China controls 60 to 80% of global production. It's a chess move that says, you restrict our access to machines. We restrict your access to the stuff the machines need to work. Then there's the AI wildcard. In early 2025, a Chinese AI lab called DeepSeek released a model that performed comparably to the best Western system, despite being trained on far less advanced hardware. It sent shockwaves through Silicon Valley. It demonstrated something the export control architects didn't fully anticipate. If you constrain hardware access, brilliant engineers don't give up. They get creative with software. They find ways to do more with less. The restrictions designed to keep China a generation behind in chips may have inadvertently pushed Chinese AI research to be a generation ahead in efficiency. The US export controls didn't stop China. They rerouted it. Meanwhile, on the other side of the Pacific, something extraordinary is rising from the Arizona desert north of Phoenix. TSMC's Arizona campus is becoming the largest foreign direct investment in American history. What started as a single $12 billion fab announcement in 2020 has ballooned into a $165 billion mega project, 6 advanced fabs, 2 advanced packaging facilities, a dedicated research and development center. When complete, it will be a gigafab cluster handling 30% of TSMC's most advanced 2-nanometer and beyond capacity. The first fab entered mass production in early 2025, cranking out 4-nanometer chips for Apple and Nvidia. The second fab, which will produce 3-nanometer chips, completed construction ahead of schedule, with equipment installation planned for mid-2026 and volume production targeted for late 2027. A third fab has broken ground and will produce chips at the 2-nanometer and a 16 nodes. TSMC has already purchased a second large parcel of land to accommodate future expansion. The US government is fueling this with $6.6 billion in direct CHIPS Act funding plus $5 billion in loans. But the real investment is coming from TSMC itself and from the gravitational pull of its customers, who are all demanding production on American soil. But here's what nobody talks about enough. Building in America is brutally expensive. TSMC's own executives have publicly stated that constructing a fab in the United States costs 4 to 5 times what an identical facility would cost in Taiwan. The chips produced in Arizona will initially cost at least 50% more than their Taiwanese equivalents. Finding qualified workers has been a constant headache. TSMC has had to hire American engineers and ship them to Taiwan for 12 to 18 months of training. And even with all of this investment, TSMC's Arizona site currently meets just 7% of total US chip demand. 7%. The gap between the aspiration of semiconductor self-sufficiency and the reality of actual production is enormous. The United States isn't alone in this race. The European Union has mobilized over 43 billion euros through its own CHIPS Act, aiming to double its global market share. India approved a $10 billion incentive program, with the Tata Group building plants targeting production by 2026. Japan is hosting new TSMC fabs in Kumamoto. Samsung is investing billions in Texas. Everyone is trying to build their own chip supply chain, and almost everyone is discovering it's far harder and far more expensive than they imagined. So what happens when the most globalized industry in human history starts fracturing along national borders? 3 things. First, chips are going to get more expensive, not marginally, structurally. The efficiency of the old model came from extreme specialization and concentration. When you duplicate that infrastructure across multiple continents, each with different labor costs, regulatory environments, and supply chain ecosystems, the price goes up. Memory prices have already surged. Some consumer memory configurations have risen as much as 4 times since late 2025. And that's before the full impact of tariffs. which in 2025 pushed the average American tariff rate to levels not seen in 75 years. Every dollar added to chip costs cascades through the entire electronics ecosystem. Your phone, your car, your data center bill. Second, we're heading toward a world of two distinct technology ecosystems, one centered on the US and its allies, Taiwan, Japan, South Korea, the Netherlands, Germany. The other centered on China and its growing sphere of influence. These ecosystems will increasingly run on different chips, built with different tools, designed with different software. They'll be semi-compatible at best. Companies will have to choose which ecosystem to design for or pay the cost of maintaining dual supply chains. One industry analyst put it bluntly. The era of a seamlessly integrated global semiconductor supply chain is decisively over. And it's not just hardware that's splitting. Data is becoming the next front. Governments are increasingly requiring data storage to remain within national borders. Cross-border data sharing is being restricted. Over half of industrial manufacturers plan to increase their use of edge computing in the next 18 months, building localized processing power to keep data from crossing geopolitical lines. The semiconductor divide isn't just about who makes the chip, it's about who controls the information flowing through them. And there's also a human dimension that doesn't get enough attention: the talent war. China faces a projected shortfall of 200,000 to 250,000 semiconductor specialists by 2027. The United States is scrambling to train enough engineers to staff its new fabs. Every major chip-making nation is competing for the same shrinking pool of people who understand how to operate at the nanometer scale. TSMC had to fly American hires to Taiwan for over a year of training because the expertise simply didn't exist domestically. This isn't a problem you solve with money alone. It takes a decade to train a world-class process engineer. The fabs are being built faster than the workforce. Third, and this is the one that keeps defense planners up at night, the Taiwan question has become infinitely more dangerous, precisely because everyone now understands the stakes. Taiwan isn't just an island in a geopolitical dispute. It is the single node through which the majority of advanced computing capability flows. A conflict there wouldn't just disrupt supply chains. It would be an extinction-level event for the global technology economy. This is exactly why the US is spending so aggressively to build alternatives in Arizona. Not because it's efficient, but because it's existentially necessary. But here's the part that most analysis gets wrong. This isn't a story with a clear winner. China's EUV prototype might be a generation behind, but it proves that technological containment has limits. America's desert fabs might be expensive, but they're being built at a pace nobody predicted. And ASML's monopoly, while extraordinary, is ultimately a fragile thing. One company in one small town in the Netherlands holding a chokepoint that multiple nuclear powers are determined to break. The real lesson of the chip wars isn't about who's winning. It's about what happens when the world's most critical technology becomes inseparable from the world's most dangerous rivalries. Remember that machine I described at the beginning, the one that fires lasers at molten tin 50,000 times per second to etch circuits a few atoms wide? It took 30 years, billions of dollars, and a 1,000-strong global supply chain to create. And now, multiple governments are trying to replicate that capability simultaneously. Not because it makes economic sense, but because they believe their national survival depends on it. We've entered an era where chip factories are as strategically important as aircraft carriers, where a single Dutch company's export decisions carry more weight than UN resolutions, where the Arizona desert and a secret lab in Shenzhen are the front lines of a conflict that will shape the 21st century more profoundly than any war. The next time you pick up your phone, remember, the tiny chip inside it passed through the most complex and contested supply chain ever built by humans. And right now, the most powerful nations on Earth are fighting over who gets to build the next one. If this reshaped how you think about technology and power, You'll want to see our deep dive into how AI itself is accelerating this arms race and why the next 5 years matter more than the last 50.